Welcome to this MADYMO online training on MADYMO seatbelt modeling. In this training we will discuss how the different components of a seatbelt model in MADYMO can be modeled. As components we have the belt webbing, the belt attachment points, the anchor, the D-ring and the buckle, and the belt retractor system, including pretensioner and load limiter. First we will discuss the belt webbing. The belt webbing in MADYMO is built up of belt segments. This can be multi-body segments as well as finite element segments. Multi-body segments are modeled with the keyword belt segment. The belt segment ends are attached to either reference spacer or a body rigid, or a finite element node in the case where a multi-body segment is connected to an FE belt segment. FE belt segments are modeled with the keyword FE model. First, about multi-body segments. With the keyword belt segment you define the multi-body segment. Within there you can define the belt characteristic. This is done with characteristic.load. A characteristic.load consists of a tensile force versus relative elongation function. You have a loading function, an unloading function, and a hysteresis slope. Besides that, you can define material damping and rate dependency. The FE belt system is modeled with FE model. For each FE belt segment, for instance the shoulder belt and the lap belt, a separate FE model is used. Normally the FE belt segments are modeled with 3-node membrane elements. For this, element triad tree is used in combination with property mem or property mem tree. The material is modeled with an elastic material model with hysteresis. This is normally material.hisiso. And also important for FE belt segments is that you can rigidize the belt ends. This is because an FE belt segment, only part of the belt webbing is modeled with an FE belt segment, where at the end it's connected to an MB segment. And in order to avoid the FE belt to collapse, to fold, you can rigidize the belt ends. For this, the keyword rigid_element is used. The material characteristic for an FE belt segment is modeled with material.hisiso. You define the density as well as a characteristic.material. Similarly to what is done for the multi-body segments, you define a characteristic with a loading and unloading slope, or an unloading curve and a hysteresis slope. It is important to define your characteristics in nominal stresses versus linear strains. In this way they can be properly aligned with the characteristic of the multi-body segment. The alignment can be done in a robust manner with using the same loading and unloading curve, both for the material characteristic of the FE segment as well as for the multi-body segments. You can do this with the keyword function usage. In this way you can scale a force versus relative elongation characteristic for the multi-body towards a stress-strain curve for the FE segment. Also for the FE segments, material damping and rate dependency can be modeled if desired. FE segments can be initialized with respect to reference space. This means that the nodal coordinates of the FE segment are defined with respect to the reference coordinate system, or with respect to a local body coordinate system. This can be done with initial.fe model. Furthermore, for FE models, for FE belt segments, one can define Rayleigh damping. This can also be done with respect to the global coordinate system or a local body coordinate system. In In case you define radial damping with respect to a local body coordinate system, it means that damping will apply as soon as the nodes of the belt segment move with respect to the local body itself. Connectivity. The FE belt segments need to be connected to the multi-body segments. This is done with point object MB. Under point object MB, one can define the nodes, so the end nodes at the center of the belt, at the end, the rigid ends. You can define point objects. These point objects are then used under belt segment, the multi-body segment, and you can refer to them. So in this way, under the multi-body segment, you connect to the FE segment. Next, we will discuss belt tyings. So we will look at the belt anchor, the D-ring, and the buckle. First, the anchor. The anchor is seen as a fixed belt end connection to the vehicle interior. So basically, it is the end of your belt system. The reference can be made to a point object for this. It means that you have the latest segment in your chain of multi-body segments. You have a point reference 2 as an attribute, which you can refer to a point object, for instance, connecting to a body belonging to your multi-body vehicle model. For anchor points, if there's no slip at the anchor possible, you don't need to define any belt tying. This means it's a fixed end to the vehicle. The D-ring. The D-ring is basically a slip connection between two multi-body belt segments. The slip means that there will be belt length transfer over the connection point. This can be defined with a reference to a point object. So for the D-ring, you can have a separate point object for the D-ring, which is referred to as point reference point 2 in the first segment from the retractor to the D-ring, and as reference point 1 under the second MB segment from the D-ring to the shoulder FE belt segment. A belt tying is used to define friction against slip through the D-ring. The buckle can be modeled in the same way as a D-ring. Again, this is a slip connection between two multi-body segments. In a similar way, you use belt tying to define your friction, the friction against the slip of the multi-body segments. The belt tying, as just mentioned for the D-ring and the buckle, is used to define the slip. This is done with a Coulomb friction coefficient, with static and dynamic friction coefficients, which means that you can model stick slip. The belt segment junction, which is in fact the belt tying, is in fact a belt segment junction. You can define it with a single point reference 1, and optional, it's possible to define a second point reference, but normally you will define only one point reference, meaning that the belt ends are joined together at one single point. For the buckle, we also have a buckle locking mechanism option. In modern belt systems, a buckle locking mechanism is often present, and the principle is that a locking mechanism allows slip from the shoulder belt, from the lap belt to the shoulder belt, yet it blocks the slip from the shoulder belt to the lap belt. And in this way, the load distribution over the upper and lower torso of an occupant is controlled, and this adds to the safety of the occupant. In MADYMO, a buckle locking mechanism can be modeled with the use of sensors and operators. Basically, you have your buckle as a belt tying, but your friction will be modeled, will be controlled with sensors looking at the direction of slip through the buckle, as well as the differences in forces over the buckle on the different segments. More details on this can be found in our frontal impact examples that are delivered in the MADYMO installation directories. Next, we move to the retractor, pretensioner and load limiter. First, we will discuss the retractor. The principle of the retractor is that it's a winding mechanism to withdraw belt webbing back into the retractor housing. It has a sensor-based spool lockup that avoids webbing pull-out when in a collision. And the lockup is mostly done with sensors based on vehicle acceleration or the webbing pull-out rate. Mostly the retractor is installed in the pillar base or in the seat. In MADYMO, the normal way to model a belt retractor would be with belt underscore retractor. In this element, there's two switch references, one for the spool switch. With this switch you trigger the locking of the retractor, and one for the grabber switch. Once a spool is locked, you will have a film spool effect, which means tightening of the belt webbing on the spool. And once the grabber switch is activated, also the film spool effect is disabled. The film spool effect itself is defined with a characteristic. It should be noted that the belt retractor is always present at the end of a complete belt in MADYMO. And this is defined with point ref 1 under the element belt. The initial state of a belt retractor means that it has free belt outlet. There's no pretension and slack is removed from the belt. A bit more on the film spool effect you see on the next slide, where a characteristic is shown. The film spool effect is modeled with characteristic.load, and it's activated with the first trigger in belt retractor, the first switch, and the second switch locks it again. The switches to lock and to disable the grabbing can be done with switch time or switch sensor. With switch time, it means that you predefine a certain time in your simulation at which the retractor locks or the belt spool effect is disabled. And with sensor-based, you explicitly model the sensors and let those detect when to trigger the retractor. Next, we will discuss pretensioners. The principle of pretensioners, you have basically two types of pretensioners. You have the retractor pretensioner and the buckle pretensioner. The idea is the same, that the pretensioner, it tightens the belt by reeling in belt material. Pretensioners can be pyrotechnic from nature or electromechanic. Mostly you see electromechanic also in the pre-crash phase, where pyrotechnic pretensioners are irreversible and are mostly used only in the in-crash phase. Pretensioners can be modeled with the keyword belt pretensioner. You have two types, belt pretensioner pay in time and belt pretensioner forced payout. Alternatively, the belt pretensioner can be modeled with a multi-body chain with a translational joint, a restraint joint and a state joint to switch on and off. We will show a bit of that later. The belt pretensioner. First we will explain in MADYMO how it's modeled with belt pretensioner pay in time. Belt pretensioner pay in time, when this is used, it means that you define a kinematic belt pay-in model. So it means that the pay-in of the belt is prescribed, and it's described as pay-in length versus time with a function. The retractor needs to be locked in order for the pretensioner to work. The belt pretensioner force payout is a dynamic belt pay-in model. This means it is force-based, and it's a force-based pay-in of untensioned belt length based on the force versus payout function. And payout is here defined as, it says payout, but basically you define in the second quadrant, meaning negative values coming back to pay-in. Since it's a dynamic model, it's also needed to define the spool moment of inertia and the radius of the spool. Next, load limiters. On the slide here, there's two mechanisms shown for load limiters. You have a ladder mechanism where the complete retractor system is shifted over a ladder, and the teeth of the ladder are deformed plastically, allowing the sliding up, and thus in this way giving out a belt at a certain maximum force level. And more modern system is the torsion bar load limiter, where the mechanism of giving belt is modeled or is designed with a torsion bar inside the belt spool. The load limiters in MADYMO can be modeled with the keyword belt load limiter, or again with a rigid body and a translational joint with switches. With belt load limiter as a keyword to define the load limiters, you can define load limit pairs. That means for each load limit pair that you define, you can define a certain load limit level. In a load limiter, you can have multiple levels, so you can have multiple load limit pairs. When load limiting occurs, after that in the unloading phase, so when the payout decreases, it will unload again with hysteresis, and for that you will define a hysteresis slope. Similar to what we saw for the pretensioner, the load limiter only works when the retractor is locked. Furthermore, it's important, if you define multiple levels in a decreasing order, that you make sure that the former load limiter level is deactivated when the next level is activated. For this, you can use switch multiport. On this next slide, you see an example of a multi-body chain representation for a retractor, pretensioner and load limiter combination. What you see is done is that the last multi-body segment is connected between two bodies, and in between those two bodies there's a chain of rigid bodies and translational joints, and each of these joints represent one of the features of the combined system of retractor, pretensioner and load limiter. For instance, the lower joint on the plot shows the retractor spool joint, which is then initially unlocked and can give way so that the belt segment can be shortened, basically meaning that there's belt payout. On the top joint in the pink square you see the pretensioner joint. This is, for instance, a joint that is initially locked, and once it's released there is a joint restraint on there that will pull the joint downward in this example, elongating the length of the belt on the spool, meaning belt pay in. And the whole system of bodies and joints as shown here needs to be controlled with switches and control logic. Next we will discuss the belt triggering conditions. In the real world you have sensors, control and actuators for a belt system. So the sensors are often sensors that detect vehicle acceleration and threshold levels for that, as well as webbing pull-out rate. Control is normally done with control algorithms inside a restraint system ECU, and the actuators you can consider the spool locking, the pretensioner firing, or triggers for the webbing grabber or the load limiter. In MADYMO, if you want to represent this, you can for the sensors use the element class sensor. So you have sensor body linac, for instance for detection of linear acceleration of the vehicle, or sensor belt or sensor joint if you work with a multi-body chain. For control in MADYMO you use switches. The switches, we have several switches, switch time as we say for simple time control switching predefined. But also switch sensor, switch logic, switch multiport and switch control system. And the actuators in the MADYMO model are basically your elements like belt retractor, belt pretensioner and belt load limiter. this is where the switches are called, and if the switch changes, then the belt retractor, for instance, will make sure that the belt spool is locked. Here you see an example of time-based triggering in MADYMO. An example, say for retractor spool locking, how can you model this in MADYMO? With time-based triggering, basically you predefine a certain time in your simulation at which the spool needs to be locked. So then you use the element switch.time, and with switch.time you can that can switch from false to true, and once that switch is used under belt retractor, then the belt retractor will make sure that the spool is locked and no more belt is payout is given. On the next slide here you see a more complex example of how this could be modeled with sensor-based triggering. Here you see the example with a sensor body linac as well as a sensor joint on the right side. Those are two sensors modeled that determine certain threshold levels in the switched sensors that are used on the second row, if you like, in the red boxes, in the orange boxes. You will see the switch sensors that detect certain threshold levels, and you see a switch logic that will make sure that initially all the sensors are true, and as soon as one of them becomes false, the switch logic becomes false. And in this example with a joint modeled, you have a state joint and the joint will be locked. So this is an example of how you can explicitly define your sensors in your model.